Example 2.3, use simple circuit methods only to determine the current I and the voltage V. As always, identify all nodes. So if I look at the nodes, then I'm going to come in, I'm going to paste my circuit, and then I'm going to start coloring them. I see here that I have a red node at the top here. And because this is the first one I'm going to color, I'm going to call this node A. And you could see here that down here is the ground. So when I look relative to the ground, this node A here has to be 12 volts. So I see that I have one more node left. And this node here, I'm going to call B. So the first thing that you should note here, this tells me here is that I have 3 nodes. And these nodes, remember, node voltages are equipotential surfaces. Okay, so the one thing that you want to pay attention to is look at that 6 and 30 ohm. They're both ends of those resistors have the same equipotential, which means that there's no height change and therefore their voltage is 0. So I would say note the 6 and 30 ohm resistor both have the same 2 equipotentials. In other words, their voltage is 0. So that means that their voltage is 0, which then tells me that the voltage of the 6 ohm and the voltage of the 30 ohm are 0. In other words, these are dead resistors that are shorted out. That means no current flows through them. So what we need to do here is that we need to remove it. So we want to be careful here, and we want to redraw this circuit now. Okay, so let's redraw this sub-circuit to remove 6 parallel to 30. So the way I would draw it here is that I would draw it like this. I'm going to make that 6 and 30 as one resistor. So then I'm going to go like this. Then I'm going to come in. And now I'm going to go down. And I'm going to place my one resistor, which is 6 parallel to 30. And then you could see then I come down and I have the 36. And now I'm going to follow the lines. So if I follow the line, you could see here is that this guy goes to 72. And this is 36. And then I have the line here, which is 9. And then I have this single wire that comes across this thing. So if I start to look at this guy, what am I seeing here? What I'm seeing here is that I have my red node right here. And so that means that the current that's going through this 36 here, right? So the current coming through here is 0. So this branch right here gets taken out. Where I gotta, oh, I missed a resistor down here. Just realized that. And this resistor is the 10 ohm. So I look at my, oops, I'm missing a resistor here again. So now if I continue my coloring to make sure that you're with me, here's my coloring. And so you're seeing that this resistor right here is now taken out. That's gone. So that means then that the equivalent circuit now looks like this. You could see that current's going to go through the 36 ohm, right? So here's my 36 ohm. And then what you're seeing here is that I have my 10 here, and then I have my 72 here, and then I have my 9 here, and then I have my wire that comes across here. So I literally removed that thing. So again, let's go through the process here. So what you're seeing here is that you're seeing this. So this is my node A, which is 12 volts. Here's my ground, which is of course 0. And then finally, I have my B node, which is this green one. Now, note that this is 2 parallel branches. So the final circuit here is what you're seeing here is that we have, there are 2 parallel branches. One is the 36 ohm. The other one, as you could see here, that it's the 72 and 9 in a parallel. And so if I start to look at the current here, you could see that the current is coming in here. And this is where we want the voltage here. And here's what you should note here, that the current / voltage we want to calculate is only on the right branch. So this means here is that you want to separate these branches. So what I'm really saying, I only care about one of the branches because of where the current and the voltage are located here. And because they have the same voltage, I'm really only interested in this. So I'm going to come here, and then I'm going to divide these guys. And here's my equivalent circuit, right? So here's my 10 ohm, here's my 9, and then here's my 72. And you can see here is that right here is I have my current I, and then I want the voltage across the 72. So again, you're seeing my colors just to make sure that we're really following how I'm breaking these guys up. So here we go. We know that this, from this node to that node, we know it's 12 volts. We know this is A, and we know this is B right here. So let's look at that. So now what I'm going to do here is I'm going to look at resistor reduction. where I'm going to compress the 72 and the 9. So then I really only have 2 resistors. So this means that I want this voltage here. Now note that because these two are in parallel, the voltage of V is the same as the voltage of the 72 and the 9. And then I want this current I coming in right here. So here we go. So this is going to be 9 parallel to 72, which is going to be, since it's 9 times 8, so it's going to be 1 over 9 times 72. That gives me an 8 ohm. And then this guy is a 10 ohm resistor. So because they're in series, then I'm going to use Ohm's law. So to determine current I, use ohms. And that guy tells me that the current I is then going to be the voltage of the branch divided by our series, which in this case is then going to be what? 8 plus 10 divided into 12, and that's going to give me 2/3 of an amp. So now I have my current. Next, I'm going to use VDR what's going on to get the voltage V, which is the same as the voltage of the 72 ohm, which is also the voltage of the 8 ohm resistor, since that's the equivalent resistance. So here we go. So then the voltage of the 8 ohm is then going to be 8 plus 10 divided into 8 times 12 volts. You compute that, and I get 16 over 3 volts. So that's the voltage of the 72 ohm.